Good morning, professors, ladies and gentlemen. My name is Yuqi Lin. I'm the master student under supervision of Professor Minxin Ye. I'm very honored to give this speech at ICSS conference. The topic I will present today is boron-doped graphene quantum dot anchored on nitrogen-doped carbon nanotube as a novel metal-free, highly efficient electrocatalyst for biosensing dissolved oxygen. The presentation will be divided into 4 parts, including introduction, motivation, result, and discussion and conclusion. Dissolved oxygen corresponding to non-compound oxygen in liquid involved in various biochemical and physiological activities. The dissolved oxygen is an essential detector of water quality and purification, reflecting the self-regulating state of the environment. The main determination method of dissolved oxygen including the iodometric, electrochemical, and optical method. Electrochemical detection is the most widely used method because of its rapid response, high sensitivity, and ease of operation. In general, oxygen reduction reaction would take place principally through 2 different pathways, including 4-electron pathway and 2-electron pathway. The classification of oxygen reduction reaction electrocatalysts can be divided into 4 categories: noble metal, non-noble metal, single atom, and metal-free electrocatalysts. Although platinum-based electrocatalysts have been renowned for its great OR activity, but the poor carbon monoxide and methanol tolerance have limited its development. Traditional metals such as iron, cobalt, and nickel had been applied for OR electrocatalysts due to its possess the great carbon monoxide and methanol tolerance despite they possess less OR activity. Although the OR performance of single atom electrocatalyst is superior than platinum, it suffers from the complex fabrication process such as sintering or acid treatment. Carbon material including carbon nanotubes, graphene oxide, reduced graphene oxide, and graphene quantum dot with superior permanence and electrocatalytic activity toward ORR. Graphene quantum dot can provide abundant active sites such as edges, functional groups, and doping heteroatom atoms such as nitrogen, sulfur, or boron into carbon material and modify their interesting chemical and electrical characteristics by modulating the electronic structure of nanocarbon. The difference of electronegativity between boron and oxygen atoms allowed easy absorption of oxygen molecules on boron atoms, which lead to the subsequent oxygen reduction caused better electronegativity. Therefore, a synthesized boron-doped nanocarbon might be a predominant strategy for metal-free carbon-based electrocatalysts toward ORR. Besides the single heteroatom doped materials, multiple heteroatom co-doped carbon materials exhibit impressive OR performance due to their synergetic coupling effect between different heteroatom atoms that could facilitate the electrocatalytic reaction of oxygen. On the other hand, it has been reported that nitrogen-doped carbon nanotube exhibit strong electrocatalytic activity for OR and enhance the absorption of oxygen molecules on the active center, therefore weakening the oxygen bonding and lowering the OR barrier. So we want to design a boron and nitrogen co-doped carbon OR electrocatalyst. However, boron-nitrogen cobalt material have the BN bond formation, which is unfavorable for OR activity owing to the compensation effect between P and N-type dopants. These 2 cases corresponding to different electronic structure totally with varying effect of conjunction in a delocalized pi system, which eventually leads to distinct OR activities. Herein, carbon nanotubes were first chosen as a metric owing to their low cost, high conductivity, and excellent stability, followed by further pyrolysis treatment at 800 degrees Celsius for homogeneous nitrogen doping. Simultaneously, boron-doped graphene quantum dot, which could provide hydrogen-rich functional group as active sites, was synthesized via a hydrothermal process. Subsequently, boron-doped graphene quantum dot were absorbed on the NCNT strongly by stirring and ultrasonication due to pipette stacking and further improving electrocatalytic ability. This is the morphology of NCNT by TEM. From the XPS result, the nitrogen has been absorbed on CNTs and the nitrogen amount is 0.5%, similarly to the EDS result. After BGQD absorbed on the NCNT, from XPS first at 398.4 eV, there are no boron-nitrogen bond had been formation. Second, they have ferritic and graphic nitrogen, which can change the electron structure and facilitate the OR performance. the carbon-boron and carbon-nitrogen bonding also can be observed, which prove the ubiquity episode on the NCNT. Moreover, from the Raman spectra, adding ubiquity onto NCNT can increase the defect amounts. For the OR performance, first, from the LSV, the onset potential of ubiquity NCNT is 0.91 volt, superior than CNTs. The optimal result shows that adding 0.5 mole of ubiquity has the best onset potential. In order to check our reaction, follow the 4-electron pathway. The disk current and read current also be measured. Using Taylor equation to calculate the electron transfer number, and the result is 3.5, indicating that ubiquity NCNT possesses a great OR performance. The methanol tolerance is a crucial issue for the development of platinum-based OR electrocatalyst. After adding methanol, there is no current difference for ubiquity NCNT electrocatalyst. The current retention of ubiquity NCNT is 93%, superior than platinum in the long-term stability test. Compared to the other graphene quantum dot or carbon nanotube-based OR electrocatalyst, ubiquity NCNT possesses highest onset potential than others. Dissolved oxygen detection were not always in alkaline medium. Therefore, we also measure the cyclic voltammetry inside neutral and acid medium. Results show that ubiquity NCNT can trigger the oxygen reduction reaction inside the neutral and acid medium, indicating that this electrocatalyst can be applied into whole pH range medium. We also measure the dissolved oxygen of the seawater, the result indicating that electrocatalysts can measure the dissolved oxygen difference with a high sensitivity of 0.011 mA per centimeter squared per ppm with a high square value of 0.99. Then we apply these electrocatalysts into commercial dissolved oxygen sensor. After turning to the Wi-Fi, the data of dissolved oxygen measurement will be uploaded to the web page. This wireless communication and continuous measurement can effectively reduce the need of human resource. At last, the dissolved oxygen measurement by the commercial electrocatalyst and the ubiquity NCNT electrocatalyst have been compared. The results show that the dissolved oxygen measurement get from these two materials is similar. Moreover, ubiquity NCNT can exert the dissolved oxygen detection precisely in a floating dissolved environment, indicating that this material can successfully be applied into wireless communication and be helpful for the development of aquaculture. So, in a summary, ubiquity NCNT can synthesize without the formation of boron-nitrogen bonding and also have a great onset potential. Ubiquity NCNT also have a superior long-term stability than platinum and also have a great retention. Ubiquity NCNT also exhibit ultra-high sensitivity than others. And thanks for your attention.